Did you write the title down? Yeah. Okay. Later. I'm so hungry right now. I can't. I just have enough energy to do this. Okay. Right. So imagine we have a capacitor, like in a camera, and it's fully charged up. It is then suddenly allowed to discharge through a resistor, like a light bulb. Let me draw this. So what we have our capacitor, and the capacitor is fully... Already? What could you possibly have a question with? I haven't done anything yet. What's your question? Is it about this?
Yeah.
What's the question?
Just a normal question.
Yes.
How do you know it's fully charged?
Because I said it in the question.
Normally,
yes. You're told it. This capacitor is fully charged. Then it is discharged through a light bulb, so the current comes out. And then you have your flash. So my question is this, if you connect, for example, an ammeter here to measure the current. So here is the time, and here is the current. What do you think the graph would look like? Think about this for a moment, and then I want somebody to give me, just think, let everybody think. Draw, think, and in a moment tell me what you think the graph would look like.
could you mean an answer?
Huh?
Meanwhile, could you answer my question?
How do you know it's fully charged?
No, yeah.
I think
yeah,
it's like this.
If it's like, how do you know how much capacity you have?
You have to be told it, or given enough information to calculate it. Yes? Now, yeah, let's imagine it's already fully charged. Okay, so we have one answer. What do you think? Okay. Anyone else? You have an idea, Grace? No? Amanda? Okay. And then Sophie? Any ideas? Yeah. What do you think the graph will look like for current and time? Any ideas? No, I haven't told you this. You need to think about it. No? Yes? No? Any ideas, Taken? No, don't care if it's in your book. I want to know if you have an idea. Good. So we have two ideas. Some people said like this. Guys, look up. Some people said this, and then somebody said this. So I'm glad that everybody had the right idea. The current will decrease. What will happen is the current will decrease like this, very quickly. Very quick. Very quick. So I drew it. Okay, now also, by the way, also notice, look here. This is a capacitor, and this one here, what's this one? It is a resistor. Yes? We have one resistor and one capacitor. So we call these a RC circuit. Time. So please note this vocabulary. RC circuit is one resistor and one capacitor. Okay? RC circuit. Can I go on? So I added in the ammeter and I measured it. So here is an example of some data. Here is the current and here's the time. I would like to draw this, but first I need you to copy this table. So you've got the table. Yeah? Got the table, everybody?
No.
Not yet? Okay. Is that yes now? Yep. Okay. So let's make a graph here. What goes on the x-axis? Time. What is the unit for time in my date? Seconds. And on the y-axis goes current. And what's the unit? I used milliamps. Milliamps. Okay, let me make this a little bit bigger for you. Alright, so what's the first time? 0. Then up to 10. Okay, the first current? 100. 70.7. 50.7. 35.4. 25.0.
12.5.
Yep.
8.84. 6.25. 4.42. 3.13.
Right, so let's make the graph here and see what shape we get. Insert chart, scatter, XY, next. Title is current against time. Time is in seconds and current is in milliamps. And this is the shape we get. So please roughly draw this. What type of graph is this, does it look like? What's the name? Shh. You be quiet. See if someone else knows. Anybody know the name of this? Chinese students who need to practice their English? No? Grace? Don't want to practice English? Fair enough. Korean students who need to practice their English? This guy down the back doesn't need to practice his English. KJ, do you know the name of this graph? Oh my goodness, you do need to practice your English? What's the name of this shape? Too fancy English. Give me simpler English. Begins with an E. Do you know if I had?
E now.
Oh my goodness, I thought you did. Exponential.
Oh, yeah.
Do you remember this in maths? The E?
I was just thinking of the E.
Doesn't matter. Do you know this word? It doesn't matter. We'll get to it in a moment. Right. So as you can see, this graph is exponentially decreasing. Exponential. Do you remember that from maths class? Look. That was this chapter. Exponential. Look up. Exponential. Exponential. Remember? As you can see, KJ, get off the phone. Are you on the phone?
No.
Alright, okay. As you can see, the graph is exponentially decreasing, which is not a surprise, because you all thought it should decrease. So we assume the graph is of this form. The current equals the current at the beginning, e to some power. It is difficult to get the information from a curved graph. We can see what the I0 is.
What's 1 over?
Yeah, we'll get to that. But what does the 1 over tau? That's a tau. This is like our k. Look, I'll get to this on the side. So our graph looks like this, doesn't it? Y equals AEKT. But because it's going down, what do I know about the k? We know that it is negative. In physics, we use this formula for I and t. I equals I0. What do you think I0 is? Initial. E, and we don't use K in physics here. In physics, we use this letter, 1 over tau. Tau. Tau.
Like Chinese tau.
No, think more like Greek letter. You know? Alpha, beta, gamma. Yeah, it sounds like a Chinese tea, doesn't it? Yes? Tau tea? No, you're thinking I'm crazy. That sounds nothing like a Chinese tea. Yeah, how to draw it. Look, it's like this. Line, and then a C.
Oh, J.
Or an upside down 2, yeah? Or a backwards J. No, yes. But I write like this.
C.
Like a C with a line.
Actually, it's like this.
I don't know which is closest. You can see on my slides.
So,
We'll go back. Can I go back? It's like
E
this.
with the edge.
I don't know.
Yeah.
Close enough. Right, so anyways. Tau. Now, what I want to do next is I want to calculate the log of the current. So if I go back to my file here and I put in another column, look up please, look. Log of I. And what's the unit? The unit is log of milliamps. So here I get equals log of this number. Now what I'm going to do is I'm going to delete this graph and make a new graph using time and these values. Actually, so hang on. Actually, I don't need to do it. I can just paste this over here.
control.
Now look what's happened. When I use time, look. That'll be a long day.
Oh yeah.
When I use time and log current, I don't get a curve anymore. What do I get? Straight line. This is much easier to use than a curve, and it's easier to draw. So log current is more convenient for us to use in our tables. Oh, so now actually, sorry, I need to change this here. This should now say here. Come on, change. Whoops. Log current. Anyways, when I use log values, I get this straight line graph. So what I want you to do,
What is to be milliamps?
and it's log of milliamps, yeah. I want you to complete, you know the table you have earlier? You see the table you have? I want you now to add in an extra row, which includes the log of the current. And then after you do that, I want you to draw. See that row there? Where's your table? No space. That's so funny. Look, you can just write it here and then an arrow. Yeah. No, just write the last row here. No, it's pretty beautiful. Okay, fine. Okay, if you want. You crazy person. Copy those values for that?
Only join the values, so.
Don't make me do something I'll regret and you'll regret. Yes, the values too.
I don't regret anything.
Maybe this is the problem.
And that's the thing, because I don't make bad decisions now.
It fell. It fell off the screen. I didn't like number 10 anyways. Thinks it's so great.
It's perfect, huh?
Just because it's perfect 10.
That's why you didn't get perfect.
9 out of 10 will do. Have you got that now?
No.
Not yet?
Yeah.
So after you completed the table, I also want the new graph as well. Here it is here, of the log current and time. Who are you talking to? Put it away. Dude, not cool. Your X and Y axes have no title. That's so not acceptable. Put some title on it, put some units on it, give it a title. You have no units. What is time measured in? Years? Seconds, right. Right, continue now. All right. So now, let me see. Next. Okay. So notice how the graph is linear. Yep. Right. So let's go back to this formula for the graph. Are we looking? I don't think you're looking, Grace. Look. We have I equals I0 e minus 1 over tau t. And what graph did this make? What's it called, this shape? What's this shape called? Exponential. What did I do to make it linear? I use log. So let's use log and see what happens. Log and log. So now I get log current equals log I0 plus log e minus 1 over tau t. Now what happens when you have a log and an e together? They cancel. So now you have log I equals log I0 minus 1 over tau t. So now you have log I equals minus 1 over tau t.
What's the value of tau?
We don't know yet. It's a constant, we don't know.
What happened to the yellow I0?
Fahad interrupted me in the middle of writing it. That's what happened. So if you just give me a moment. Plus log I0. Alright. So now I have log I equals minus 1 over tau t plus what color I will go with this green, log I0. Please compare it to this formula. Y equals m x plus c. What I'm trying to get you to see is if I use log I and if I use time, that's the reason I get a straight line, because the form here is the same as the form here, where y is like log I and x is like the t. So now you can actually see that the slope, what should that equal? Minus 1 over tau. Now, this much?
Yeah.
This process is very important and very common in the, not only the exam, but in physics. We will do this process again in a later chapter. Yep. Linear is the noun. It means a line. Linear. What you've done is you've changed an exponential into a linear. Does anyone know the verb? And I'll give you a clue. Linear is the noun. What is the verb for this? Good try, not quite. Linear? No.
Can I say lining?
Lining? No. I like it. So,
Okay.
the verb that means go here to here, that's linear rise. Yeah, that's the verb. It means to make it a line. To make it linear. Linear means line. See, learning English can be interesting.
No.
Yeah. Although I do prefer your verb, KJ, lining. Like it. Or maybe lineify. What else could we have? No, I'm all out. All right, can I go on?
Yeah.
Not yet? Okay, yeah? Right.
10 seconds.
10 seconds. Seriously, dude, you're getting exactly 10 seconds.
5, 4,
No, too fast.
2,
Steven,
I'm done with that.
you can use this.
Ella.
Not element, the biggest integer.
Use ln. Do you have an ln button?
Yeah.
Use that.
About the compound.
No. We make it linear. Always. Because, yeah?
You can use the derive opposite.
They will suggest they will be saying.
Hold on, he's asking me a question. And I don't think he was finished. So be quiet. Yes.
The longest.
The long S.
Yeah.
What are you talking about?
This.
Oh, later. We haven't done that yet in maths or physics.
Now what?
So I'm not talking about that. Forget about it. Yes, now.
They will say in the questions you have to convert or something. No.
Yes. They will use language like make an appropriate graph or make a suitable graph.
Make a straight line.
And often they might even say by using log, make a... Right, continuing. So we've just seen what happens when you put log on both sides, you get this formula, which you wrote down. Yeah? Did you write that down from here?
Yeah.
Yeah. Well, this one.
what's the value?
That different?
No, that's exactly the same. Log I equals minus 1 over tau t plus log I 0. Log I equals minus 1 over tau t plus log I 0. It's the same.
What's tau?
I haven't gotten to that yet. I'll get to it. For the moment, it's a constant. And so, we have y equals log I on the y-axis. What goes on the x-axis? Yes, speak up. Yeah. What is it? What's t? What does it represent? Time. The slope, the gradient, is minus 1 over tau. And what is the intercept? The c? Log I 0. It would be helpful to write this second line down if you don't have, no, the meaning of each term. This line, Fahad, this, and this. Sorry if it's expecting too much of my students to write down what I give them.
I don't heard gradient slope is this.
Did you write down intercept?
I know.
No, but write it
Because I
down.
explained it.
Write it down, but you'll forget it if you don't.
Because this is rough. I need to like fencing the notebook.
If you say so. Okay, you got this?
No.
Yes?
Yeah.
Okay. So if we have this formula, by using log, we can make it into this formula, which you have. Yes, we have this. Now, what do you think about voltage? What would the voltage graph look like? Against time, yeah. If we have time and voltage, what graph will that make? The same, actually. It will also decrease.
When we don't have the
Yeah, no, if I replace this ammeter instead with if I put a voltmeter here and have voltage and time, you get the same graph. It's also decreasing. And what about the charge, Q? What about the charge? What do you think? Charge. Also decreasing. In fact, it's nearly the same formula for Q and nearly the same formula for V. Oh yeah. Got it? Yeah? Alright, so, finally, the tau. So, the tau is actually called the time constant. And you can find it by using this formula, which we actually saw earlier. Tau equals minus 1 over the slope.
hold on. The slope is 1 over half.
You can rearrange it.
If you don't have a slope, then you can find it else.
Yeah, exactly. So once you make the graph, you can get the slope. Once you have the slope, you can get the tau. Time constant equals minus 1 over the slope. Okay? Yes? So what exactly does this time constant mean? Well, let me tell you. Oh yeah, I forgot to say. There's actually two formulas to get the time constant. This first formula, you use it if you have the graph. Okay? But you can also get it by using this formula. The resistance multiplied by the capacitance actually gives you the same number. Resistance? Yeah. From the first step. Oh, Chambers, KJ, don't kill me now. This resistance here multiplied this capacitance. So some questions, yeah, multiplied. Or C. So some questions give you a graph. And if you have the graph, let me see the next graph. Yeah, you can use the slope to calculate this. But if you don't have the graph, if you know the or and the C, you can use the second formula. Then the same answer. Okay? It depends what you have, on what you have. Okay. So what exactly does the time constant represent? Well, the time constant 5 of them is how long it takes to discharge.
Time.
So for example, look, no, wait. Don't write just yet. Don't write just yet. If the time constant is 1, then it takes 5 seconds for the capacitor to discharge completely. If the time constant is 2, then it takes 10 seconds for the capacitor to discharge, fully lose its charge.
I thought it was a constant. Why is it now changing?
Constant for the capacitor. So it's a different number for each circuit, but it would be the same for the whole problem. So now you can write it down. So of course, what is the unit here? What's the unit then? It's going to be seconds. No surprise, the unit is seconds. Okay.
So it means 1 time constant equal 5 seconds?
1 time constant is 1/5 of the discharge time. The time to discharge. Do you know this word discharge? Discharge means lose the charge, to have no charge. So, for example, here, if the time constant is 1, then it means the time to discharge is 5 seconds. This means on your graph, I'll show you here. Where's your first graph? This one here. It means the time to get to 0 is 5 seconds. If the time constant is 2, it means it takes 10 seconds to get to 0. If the time constant is 3, it'll take 15 seconds to reach 0. Yes? Question? What's your question? Yeah?
This one, I don't know, this one
Yeah.
is for low.
This graph or also for this graph? The same.
If you know the graph,
You can know this number. Yeah. This is if you have the graph, and this is if you have or and C. Now what I was saying to Amanda is if this number here was 1, if tau is 1, then the time to discharge equals 5. So what I mean on your graph is the time here when it gets the, where's the first graph? What I mean is it takes 5 seconds to get to 0. If tau is 2, like in this graph, it takes 10 seconds to get to nearly 0. That's what the time constant means. Yeah? Okay. Right, let's have a look at a question. Just one example. Yes, can I go on? You have this?
yeah.
So what I want you to do is to copy this table. I'm using milliamps and milliseconds.
Is that one?
No, this is an example I want to do now, but I would like you to copy this table.
Oh,
Huh? 540? What? Where's 540? What are we talking about? Oh, what the heck is this? Sorry, that should be 500 here. Here, this is 500. This one, 500. $500 here.
You sure about that?
1,000,000% sure. Do you have the table? I just want the table right now. Yep. You got the table? Yes? Great. So, no, hang on. I want to reuse this graph so I don't have to make a new one. Right, so what's my time in? Milliseconds, wasn't it? So I start at 0, yes? And then I go up in tens, isn't it? Okay. And then I'll put my current here, I. And what's the unit? Milliamps. Let me just get rid of this for a moment. Okay. And what's the first value?
100.
Yep.
841.
Wait, 100 is the first one?
Yeah.
Oh, sorry, that should be 1000. Oh, so now the question is easier, huh? 841
707.
707
595.
595 500
420.
420 354 297 250 210 177. Okay. What do I put on the x-axis? Time in... What the heck? Time... How do I can't see, it's too small.
Just type one thing and see where it
See what happens? Nothing's happening. Oh, hey. Milliseconds. Milliseconds. Right. Okay, so what do I put on the x-axis? Time in milliseconds. What do I put on the y-axis? What do I put on the y-axis? What's it called? That's the unit. What's it called? What do I put? What do I put on the y? Current? No. We should only use log current because that makes a nice straight line for us. Okay? So now in the question I said, graph this in an appropriate manner. Appropriate, a suitable way. In physics, listen, in physics you really, really want your graphs to be straight lines. If you can make it a straight line, this is what you should do.
But if you don't, you can still get the slope.
No, you can't get a slope from a curve graph. Has to be a straight line.
Taking the time.
Oh my goodness, yes, but that would be so long and difficult. Right, so let's calculate the log here.
You said you can't.
When you have 2 hours to do an exam, you can't, okay? Right.
We did it in Nigeria.
Well, congratulations to you. Oh, look at that graph. It's a straight line. Right, so what should we calculate? We should calculate the slope. I would like everybody to use my graph to calculate the slope. So what is the slope? What is the gradient? Anyone got a number for me? It should be pretty small.
Minus 0.017.
Okay, so let's go with that, KJ.
Minus 0.017.
Here, look. The slope equals, so what was the height? What was the height? KJ? KJ! what was the height here that you used?
6.73.
Yeah.
6.21.
What's it about? 1 point, 1 point. Everybody,
0.52.
everybody, look up, look up, look. I am just asking for the height here. What is the height?
0.52.
0.52.
Yeah.
Are you sure?
There's
What the?
1
Whoa, 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 whoa. What's going on?
Stop it,
I
stop
can't stop.
it.
It's
Change the application, change the application.
You left out.
Yeah.
no. It's I was dragging it. Oh wow. Oh. Right. Well, actually, this isn't so bad. So the height is nearly 7 down to
6. No.
down to getting there 5 something. So what? About 5 to 7. So what was that like? 1.8? What was it?
1.7.
Okay, thank you. If I had, what did you get? You got minus 1.7 because it's going down. So we need a minus.
Why is it?
Because the slope is going down.
Yeah.
Negative slope. Because I can see it's going down. So I need to put a minus here. Because it's going downwards.
No, I don't want to ask the minus. I just want to know how did you get the 1.7.
Okay.
You can minus the values, you know?
Yeah, what I did, Amanda, was this height minus this height to get this number is 1.7.
Yes.
7
6
minus 6
times.
or 7 minus
7 minus 5.
You can, 6.90 minus.
Yeah, that's it.
5.1 something. The highest value minus.
No, not again. Stop. Ah, never mind. Look. Where's your graph? Show me your graph. Show me your graph. Okay. So I did this number minus this number. I want the height of this triangle.
Yeah.
So you make it a triangle and measure the height and the base. You got that? Taking, do you understand what I'm doing here? Yeah. So let me see your graph. What I did was, yeah, you make a triangle. You know triangle? Great, good for you. So make a triangle here and a triangle there. Okay, so it's this height. That is 1.7. Now, how big is the base, KJ? What was the base?
It depends on what you choose, actually.
The base was
10 of course.
No. This is delivered for me at the reception.
really reception here.
Yeah.
I'll go get it. Close the door after you. What's the base? 100. Yes, 100. 0 to 100. Can you see that? Amanda? This is 100. Here to here is 100.
Yeah.
Yeah? Okay, so this is 100. Now, what's the unit for current? What unit am I using? Milliamps. So milli is 10 to the minus 3. And what am I using for time? Milliseconds. What's milli? 10 to the minus 3. Yes? So they cancel. Okay, so KJ, what did you get here? Minus 0.017 amps per second. What does the time constant equal? Minus 1 over this value. So what does that equal, KJ? It's going to be a pretty large number. Yeah.
Oh, 57.8.
57.8 seconds. So how long will it take for this capacitor to fully discharge so that there's no current left? how long will it take?
Approximately a minute.
Oh no! No, no, it'll take 5 of these, remember? So the time to discharge will be almost 5 minutes. How much will it be? KJ? 4 minutes and how many seconds? 55 seconds about?
Yes.
Something like that.
54 seconds.
54 seconds.
So if that was in a camera, so it would take 5 minutes for the flash to go.
No, no, no. That's the discharge time. That would mean the light would be on for 5 minutes. So this wouldn't be a camera, because the camera would discharge very quickly. The light is bright for a very short time, you know, milliseconds. This would be something that is discharging slowly, possibly some electronic device for a computer or a circuit like this. This wouldn't be a camera. In fact, this would be something that would be in a computer for sure. Sometimes, you know the way. Oh, no, never mind. I'm going to get distracted if I talk about this. Okay, so what else do I ask for? Did I graph it? Yes. Did I get the time? What's wrong? No. Did I graph it? Yes. Did I get the time constant? Yes. What's wrong, Grace?
No, nothing.
What are you talking about?
Because the Grace said I move, and I said don't move. There, move
Yeah.
yourself.
Try not to move.
Yeah.
Try not to move. Nobody move. Yes? Right. Did I get the graph? Yes. Did I get the time constant? Yes. Do I know how long until it fully discharges? Yes. Next is, what is the value of the resistor? Oh, delete this last question. What is the value of the resistor? So what formula can I use? I can use this formula. So the resistance equals time constant divided by capacitance, which equals 57.8 divided by, and it's a 200 microfarad. 200 micro. Yeah?
Right, it's not here.
200 times 10 to the minus 3. So what is this here, KJ? Yeah, look, Amanda, millifarads. 200.
But how did you get the formula?
This?
Oh, yeah.
I gave it to you 10 minutes ago.
Yeah. 289.
289 ohms.
Very round figure.
I made up these numbers, that's why. Here. Oh, something's coming up on the screen. Can you, what do you need? Sorry. This is it. Huh?
4 minutes 49 seconds.
Whatever. Whatevs. Right. Do you have this, Amanda?
Yes.
Right, now let me just fix that as it should have been 1000 and here 500. Alright, this question here. Now relax, KJ. Relax.
I opened it.
Yeah, that's fine. That's fine. Yeah, that's it, yeah. Just stay calm now. This question here, in the final exam and the end of semester 1 exam, there's always one graph question. Fahad, put that away or I'll break it. I will. What did I just say about the final exam?
It's always a graph.
One graph question.
Yeah.
Grace, please. There's always one graph question in the final exam. So far, we've only done 2 lessons that require a graph. This lesson, and what was the other lesson? Velocity time graph.
I prefer that one.
Yeah? You prefer this one?
Yeah.
Well, you can't actually choose. So, what I'm saying is, every exam, since the first exam, always one question has a graph. So far, you've only done 2. Okay? So, if you just think about this for a moment, in your end of semester 1 exam, there will be a graph question. You've only done 2 graph questions. So, figure it out. It's either going to be this one or velocity time. No, there's never 2 graph questions. There's only one graph question in the exam. Okay? I don't know. I'll upload this, question here. Whoa, dude. Does anybody want to take a picture of this, or will I just upload it on Moodle? You can get later.
It's not completely.
It's ugly looking.
Wow, so much.
Sorry. No, it's this. No, it's not.
Million things. One question only.
Yeah, one question only.
What?
Question 1, A to I.
I say it equals
This
2
is
questions.
good. Does our graph have to be accurate?
What do you think I'm going to say? Yes, it does. Now, if you want, KJ,
Could do it on Excel.
you can do it on Excel, but of course you can't do that in the exam. So if you have trouble, you should practice with pen and paper. If not, you can just throw it down in Excel. Question?
No.
All right, let me stop this now.
No.